Hello, Ashok.
Hello, can you hear me?
Absolutely.
Can you hear me? Let
I,
it be
I, I
charged
can, I can, I can hear
after
you.
some time.
I don't know the others.
Hello? Hello? Can you hear me? Hello?
Hello.
Hello? Hello?
I can hear you. I don't know the
Hello?
others.
Yes, sir, we can hear you.
Hello? Hello?
Yes, sir, we can hear
Hello?
you.
চার্জিং হয়নি আপনার না না এখন ঠিক আছে ठीक है नो प्रॉब्लम हाँ हमको वॉइस नहीं सुनाई दे रहा तुम थोड़ा कुछ हेलो हेलो बोलो हमारा उसमें ये जो हमारा ये है ना ये ब्लूटूथ वाला हाँ पर हाँ तुम्हारा आवाज नहीं आ रहा है हमको तो हो सकता है चार्ज नहीं हो अभी तक मैं थोड़ा सा चार्ज कर रहा हूँ अभी तो कितना टाइम है अभी 6 मिनट है नहीं अगर हमारा वॉइस नहीं आता है तो तुम स्टार्ट कर देना ठीक है ओके स्टार्ट ओके 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 Hello?
Hello, sir.
Hello? Hello?
Hello. Yes, sir, we can hear you.
একটু সেটিং একটু প্রবলেম আছে, একটু সেটিং থেকে ওরা না তো চলিয়ে দেবে।
এটা কিসে করো তুমি, শুনছো এটা গুগল?
না, গুগল, হ্যাঁ ঠিক আছে।
এটা লাগাও কি এটা কিছু?
না না, ওটা দিয়ে চলবে, এটা 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 ব্লুটুথ তাই চলবে, এখন একটু পরে। হ্যালো? হ্যালো?
Hello.
Priyanka, you may start. You may, and George, you may introduce yourself, and Priyanka will start. There is some problem in my voice, so please, George, introduce yourself, and Priyanka will start your recording.
Okay, sir.
Device add হচ্ছে না।
তুমি ব্লুটুথে
হ্যাঁ,
করছো তো?
ব্লুটুথটা on, হ্যাঁ, Bluetooth।
Or we can't hear you.
George, sir, we can't hear you.
হ্যাঁ, এই যে।
Well, I'm terribly sorry. I forgot to well to have my microphone. Okay, so I'm not. Can you hear now me?
Yes, sir.
ঠিক
Yes,
আছে।
sir.
Hello?
Okay.
Can you hear me?
Yes, sir.
না, আওয়াজ আসছে না।
Okay. Shall I start?
Yes, Priyanka, please start. ঠিক আছে, ও করছে। He's telling.
Mr. George, please start.
Okay, thank you. So I am György Bánvölgyi from Budapest, Hungary. I have a master's degree in chemical engineering at the Veszprém University in Hungary, and I have a second degree to be a patent attorney as well. I am a senior process consultant for the time being. My experience covers processing of bauxites of different types and grades. Uh, I carried out quite a few techno-economical evaluations leading to process concepts and feasibility studies. I have coordinated of research and development projects and I was involved deeply in these kind of projects. My experience covers the environmental aspects, the utilization of bauxite residue, prevention and removal of scales. I published about 50 papers. I am the principal inventor and driver of the so-called improved low temperature digestion process. Thank you.
Thank you, sir, for your introduction. Now I am starting the presentation.
Ladies and gentlemen, I am György Bánvölgyi, Senior Process Consultant from Budapest. The title of my lecture is Alumina Plant Scaling, Types, Reaction Mechanism and Composition. Let me just skip my biography since I believe you have been aware of that. The content of my lecture is mechanism of scale formation, desiccation product scale is the model, types of various scales, equilibrium solubilities, prediction of scale types, composition of different alumina refinery scales, reaction mechanism considerations, and finally conclusions. As you know, liquids and slurries are processed in the alumina refineries. The liquid phases have complex compositions, so have most of the solid phases, such as bauxites and bauxite residues. The temperatures and solid contents are other characteristics that vary at different places of the Bayer process. The abrasive effects and scalings cause most of the headaches for the operators. The objective of this presentation is to provide an insight to the formation mechanism of various scales of alumina refineries. The scalings have several drawbacks. The scales reduce the inner diameters of heat exchangers tubes or other tubes may clog preheater tubes, reduce hydraulic and thermal performances. The thermal conductivity of sodalite is 0.5 watt per meter Kelvin. However, that of carbon steel is greater by almost 2 orders of magnitudes. The scales need chemical and or mechanical descaling, which is troublesome, sometimes incomplete. Spare equipment must be available and they incur extra costs. You will see that several types of scales exist. Here is a schematics which shows the formation of DSP scale as a model. This is the tube wall. The other part of this tube is actually scale, and here is the thin boundary layer. The temperature of saturation of a steam is represented here, and the throughout the tube the temperature decreases and decreases at much more extent through the scale, and there is a difference of the temperature between the boundary layer and the bulk of the fluid. The velocity of the fluid is actually zero at the wall, therefore the residence time of the material is practically infinite. The concentration of silica is equilibrium per definition at the wall and in the bulk of the liquid is significantly higher. The chemical reactions in general can be described if the equilibrium concentrations of the reagents and products, reaction equations, stoichiometry, reaction kinetics, reaction mechanism, and possible transformation of one modification to another one are known. Let us start with reactions of soluble alumina and reactive silica minerals. Here is the picture of the equilibrium solubilities taken from Jan Kotte paper back to 1981. These lines represent the gibbsite equilibrium solubility at various caustic concentrations. These lines describe the boehmite solubility, and there are some information about the diaspore solubility, all in the function of the temperature. And here is a Bayer cycle of a low temperature digestion refinery. Actually, it is Bauxilum in Venezuela, South America. And let me emphasize that at this point, the liquid phase is able to dissolve some alumina. However, the liquid phase is supersaturated for boehmite. This graph is taken also from Jan Kotte, and you can see that the overall reaction rate starts at about 100 degrees centigrade, a little bit at higher temperature. Kaolinite, boehmite starts dissolving at about 160, 180 degrees centigrade, and diaspore somewhere higher than 230 degrees centigrades. And you can see that at certain point the overall reaction rate slows down and a diffusion conditions are met. Here are the principal reaction equations. What you obviously know, this reversible reaction is the dissolution of gibbsite and the precipitation, the dissolution reaction of kaolinite, the formation of desiccation product from sodium aluminate and the dissolved silica species and so on. This figure shows the silica solubility at different temperatures. You may see that a little bit funny form of the silica solubility. This form is most probably due to the fact that different minerals are in equilibrium with the dissolved silica. This graph is taken from a report of mine where the dissolution of gibbsite and kaolinite and formation of desiccation product was investigated with a high reactive silica Hungarian boehmitic bauxite at about 105, 109 degrees centigrade. There was a different range. It means that at lower temperature, the so-called kinetic range can be found, and at higher temperature, the diffusion range. As briefly mentioned, subsequent to dissolution of gibbsite and reactive silica, the desiccation product forms with the following steps. Out of the sodium aluminate and sodium silicate species, sodium aluminosilicate ions form, then amorphous material, then zeolite A, sodalite, and finally cancrinite. This investigation was carried out at 65 degrees centigrade when all these steps could be clearly detected. These reaction equations describe the formation of pseudo-boehmite and boehmite, the transformation of goethite into hematite. You can see that the goethite reacts with the hydroxide ions, ferrite ion is formed, and finally the hematite is the final product. Here are the reaction equations of anatase, also the perovskite forms via sodium titanate. The key of the formation of scalings is the supersaturation of intermediate anions of consecutive reactions. We briefly discussed the formation of gibbsite and possibly boehmite through aluminate anion, the formation of desiccation product through silicate anion, formation of hematite through ferrite anion, formation of various titania scales through titanate anion and formation of, for example, carbonate apatite through phosphate anion. Here in this lecture, the so-called growth scales are discussed. In the so-called red side, side is the principal scales, and at certain places sodium fluoroarsenophosphate vanadate can be found. Here is a list of various titania containing scales which can be found in the high temperature digesters. Perovskite, calcium, magnesium, titanium, iron, aluminium, oxyhydroxide, cafetide, hydric acid, and calcium aluminohydrogarnet. The composition of titania containing scales are sometimes extremely complex. They depend on the composition of bauxite and the liquor, the temperature, and addition of calcium or other calcium oxide. Let me go further to the process technology, the feedstocks and scales of some alumina refineries. The investigation of the scales goes back to 1971 when the the scales from the Almásfüzitő alumina plant were investigated thoroughly. The bauxite was boehmitic bauxite, however, a fairly large amount of available alumina was in gibbsite, and some were found in goethite. About 40% of the iron oxide was in goethite, the rest in hematite. Some predesiccation was carried out for 6 hours at 90 degrees centigrade. The digestion was so-called single stream digestion. The digester lines consisted of 5 vertical shell and tube heat exchangers heated with flash vapor, 2 autoclaves heated also with flash vapor, and 5 autoclaves heated with live steam, and they provided the retention time of about 1 hour at 225 degrees centigrade. Here is the chemical composition of the digester scales. You can see that there was a significant change in the composition of the silica content at about 145 degrees centigrade. The silica almost diminished, and the amount of iron became dominant. The soda and the next slide shows the mineralogical composition. I am sorry that this table is populated so much. The sodalite and to a lesser extent cancrinite comprise the main constituents of scales in the preheaters at temperatures up to 140 degrees centigrade. At temperatures higher than about 160 degrees centigrade, cancrinite becomes dominant over sodalite. The sum of sodalite and cancrinite significantly decreases in the autoclaves operating at 150 degrees centigrade and higher, since the transformation of reactive silica finished. In the autoclaves at temperature of 145-166, boehmite deposits can be found due to the local supersaturation of sodium aluminate for boehmite. At higher temperatures, the liquor becomes unsaturated and dissolves boehmite. The goethite to hematite transformation starts at about 160 degrees centigrade. The hematite becomes the principal iron constituent of the scale, while goethite content gradually diminishes. The hematite-goethite ratios dramatically increase at temperatures higher than about 180 degrees centigrade. These observations support that the conversion of goethite to hematite takes place via liquid phase. Calcite and possibly dolomite and anatase react below 140 degrees centigrade. Perovskite and calcium, magnesium, aluminum, titanate compounds appear in the scales formed at higher temperatures. Some bauxite particles were entrapped in the range of 90 to 140 degrees centigrade. The next refinery is the Magyaróvár Alumina plant, Motim, also in Hungary. The bauxite composition is presented on the following sheets. Tube digester comprised the digestion equipment in this plant. This was operated with single stream digestion. 15 horizontal tubular preheater units heated with flash vapor and live steam condensate, then 4 also horizontal tubular preheater units heated with live steam, and another tube for the retention time for about 10 minutes. And after the 6 preheater unit, 2 vessels were installed to provide 12 minutes retention time at about 145 degrees centigrade, and after the 9th preheater units, 1 vessel for 6 minutes additional desiccation at 180 degrees centigrade. The digestion temperature was 240-250 degrees centigrade. Here are the chemical composition. You can see that the titania and mineral containing minerals are characteristic for the scales. The bauxite was a typical high silica bauxite in Hungary. I'm sorry that this table is populated. Also, sodalite and to a lesser extent cancrinite comprise the main constituents in the tubular slurry heat exchangers at operating temperatures up to about 150 degrees centigrade from previous experience. The vessels, which provided retention time of about 12 minutes at about 145 degrees, significantly reduced the sodalite cancrinite scale in the preheaters, operating higher temperatures to a fraction. A temporary boehmite supersaturation caused boehmite deposition at the temperature of about 145 degrees centigrade. The calcium-magnesium alumina titanate compound has been found in the largest amount in scales formed at temperatures higher than 164 degrees centigrade. The amount of hematite is significant at 140-150 degrees centigrade and higher temperatures. The goethite is negligible. The hematite-goethite ratio is about 10 times greater than in bauxite. This supports that the goethite-hematite conversion takes place via liquid phase. This is why hematite deposits. The calcium, magnesium, alumina titanate, sometimes perovskite, appear in scales. Rutile can survive the digestion process because it is found in the bauxite residue. A significant amount of hydroxyapatite and hematite have been found in scale where the calcium hydroxide additive was added at the digestion temperature. The next refinery is the Bauxilum, Venezuela, where gypsitic bauxite is processed with a digester of typical low temperature digestion of 145 degrees centigrade. The great amount of silica is in quartz. The reactive silica is almost negligible. The predesiccation was applied at 98 degrees centigrade for about 10-11 hours. A conventional double stream digestion was applied. Some 90% of the test tank liquor was preheated with fresh vapor, and then finally with live steam up to, as mentioned, up to 170 degrees centigrade. Here is a picture taken from a 1200 square meter horizontal preheater. You can see that at several cases the scales left the tubes and clogged the tubes. Here are pictures of the live steam heater scale. These scales were taken after only 3 days of operation, and this is the front view which was in contact with the test tank liquor, and that is the rear view which was in contact with the tube. Since the thickness of this scale was almost 3 millimeters. Therefore, there was a possibility to slide these scales and take 3 layers of the scales. Here is the chemical composition of the live steam heater scales, the digester scale, last flash tank and washer overflow pipe scales, and also sample was taken from the bauxite and the bauxite residue as well. As mentioned, the surface of the scale which was in contact with the test tank liquor consisted of primarily sodalite. Here you can see the rear side of the scale which was attached to the inner wall of the heating tube was only 3 days old. The amount of cancrinite increased at the expense of sodalite. It obviously formed from sodalite. The uneven surface of the scale, which was in contact with the test tank liquor, looks like ocean waves and suggests turbulent flow. You can see that there is no cancrinite in the bauxite residue, only sodalite. This also confirms that at the conditions of low temperature digestion, sodalite is the primary mineral that is formed. The scale from the digester autoclave consists of cancrinite and boehmite. Sodalite is missing. This confirms the transformation of sodalite to cancrinite over time, even at relatively low temperature of the digestion, that is 145 degrees centigrade. Boehmite is formed due to the supersaturation of dissolved alumina for boehmite, as it has been mentioned. Meanwhile, sodalite and boehmite were deposited at first. Fine bauxite residue particles may have been trapped in scale. The most characteristic constituent of the flash vessel is boehmite. The aluminate in the liquid phase is supersaturated for gibbsite and boehmite. Boehmite has probably been precipitated directly from the liquid. Another constituent is sodium aluminohydrosilicate, sodalite and or cancrinite. The cooler the flash vessel, the more boehmite and the less sodium aluminium hydrosilicate are found. A few percent of bauxite residue has probably been entrapped in this scale as well. The scale, which was taken from the overflow type of washer number 1, is almost pure gibbsite. The supersaturation for gibbsite is evident. At this temperature, formation of gibbsite is favored. Just for your information, here is a pattern of the rear part of the live steam preheater scale. What you have seen, the picture of the rear part here is the quantitative mineralogy. The XRD pattern was assessed by István Sajó, the well-known expert of the quantitative mineralogy. Here is the reaction mechanism of the reactions, what we have discussed. The kaolinite, when it dissolves, dissolved silica and dissolved alumina is formed. When the gibbsite dissolves, also the sodium aluminate is dissolved, and out of these two species, sodalite and later possibly cancrinite is formed. The dissolved alumina, sodium aluminate, can react further, and at certain circumstances, boehmite, pseudoboehmite, and then boehmite is formed. This is characteristic at about 140, 150 degrees centigrade and some higher temperatures. The conclusions are following. The important factors of scale formation in the Bayer process are the following: the fluid velocity in the bulk of solute, the direction and intensity of heat transfer, temperature, factors should be considered in a complex way. The species which play decisive roles in scale formation are intermediate compounds of consecutive reactions. The driving force for the mass transfer that result in scales is the difference between the bulk and equilibrium concentrations. After formation, scales may remain in situ for even long periods, or can transform one mineral to other. Solid particles can be entrapped in scales. The study of scales, along with reaction kinetics, is a useful tool for understanding the mechanism of several reactions. Here is a reference where you can find most of the sources of the information which was presented here. Thank you for your attention. Your questions, comments are more than welcome. Ashok, your microphone is not working.
Sir, please unmute yourself.
Let me see. Yeah, can you hear me?
Yes, sir.
Yeah. So now the session is open for discussion and questions and answer. And George will answer online these questions. Please start your questions. Hello? Any question?
Yeah, one question from my side. This is Krishna.
Yes. Yes. Yes.
That's so good morning to everybody. It's maybe good afternoon India time. The scales formation mainly, how these proportionate to the That's one thing I already explained about the transmission of the scales, and it is going to give bad effect to this. But one thing is I surprised how this is going to cost to the effect, how majorly, what the percentage of effect to the cost to the plant, or maybe in the cost point, point of view, OPEX point of view, how the cost, especially the calcium, and you mentioned about the calcium and magnesium and some silicates, it's going to give the major effect to the plant operations. That how it is going to affect to the cost point of view. Of course, that the parts is going to damage frequently. You should be repaired, should be replaced. It that's 100% agree. And the flow also reduced. The flow and heat transfer also reduced. That we understand very clearly. How much cost effect to the plant overall?
Well, sir, well, your question is a really complex question because the amount of scales highly depend on the composition of bauxite, obviously on the process parameters, whether there are additives added to the bauxite or during the digestion. If so, where, for example, a calcium oxide is added, that's a major difference. If the calcium oxide is added just to control the phosphor, in that case, maybe about 0.5% of calcium oxide is sufficient, and this calcium oxide or hydroxide is added before the digestion. But there are other process technologies where the it is an attempt to replace the sodium component of the desiccation product to calcium, and in this case, in most cases, the calcium oxide is added at the digestion autoclaves or where the slurry reaches the digestion temperature. And obviously the composition of the gibbsitic bauxites and the boehmitic or diasporic bauxites are substantially different. So I don't think that a general figure can be given to you. My understanding, this should be studied on a case by case basis. That's my understanding what you have raised.
Yeah, understand. I think what is the best to optimize the percentage of calcium can be allowed. Maybe we have some problem in the. I think maybe Dr. Nandi Sabis might be knowing about the Madan. We face the calcium problem. Remaining rest of the world, we didn't face any calcium problem. Yeah.
To increase the digestion efficiency, sometimes they add CaO and for better reactivity. So calcium is added in some of the refinery in the form of lime. So this is all depending on type of bauxite and depending on the digestion efficiency and caustic consumptions. So George was telling in some plant we add 0.5% of lime, and some plant we don't add any lime. So it's all depends on the plant where lime is added. So this calcium goes into basically information of scales.
Well, what I would add that you probably aware of that while conversion of goethite to hematite can be facilitated with the calcium oxide addition. And this, however, it's been detected, I would say, through these analyses what have been presented in my lecture. However, this reaction starts, let me say, somewhere at about 150 degrees centigrade. However, this uh, transformation from goethite to hematite facilitated by calcium oxide is well, most significant somewhere at about 200 degrees centigrade or rather higher temperatures. So it can be tested in laboratories. In general, I am in favor of carrying out kinetic tests, uh, which may allow the addition of calcium oxide at different temperatures. So, in, unless someone is deeply understands your particular problems, I am not in the position to give you a right answer for your particular problem.
Okay. Thank you. I understood. I logically understood. Thank you.
Any more questions? Phil, do you have any question? Hello? Any more questions from?
Somebody's calling maybe.
No, we are waiting for more questions. If there are no questions, we can say thanks to George. And this presentation, please. This presentation, please.
Can you arrange to send that presentation so that we can have something like go
Yes.
inside,
All the presentations which are given on IBAAS lecture series are available on IBAAS website. You can download this presentation. The Priyanka of our office will download this presentation on website, and you can take it upload from that website. She will upload and you can download from the website.
Okay, thank you.
Okay. And actually what he says correct is from goethite to hematite conversion, part of alumina logged in goethite can be released. But that is happening mostly on high temperature alumina plant. For low temperature 145, goethite does not convert into hematite. And the alumina logged in goethite is being lost. So this is what basically lime is added mostly in high temperature alumina plants.
Yeah.
And there is a causticization also done to recover part of caustic soda from the red mud, from bauxite residue. So by these two processes, there are some calcium, lime is being added in the alumina refineries. So lime is also one of the ingredients in alumina production.
Yeah, it's required.
Okay.
That's correct. Yeah.
Okay, thank you.
Well, I'm sorry, just one sentence that with this goethite hematite transformation was extensively investigated by my colleagues, for example, Dr. Károly Sojmár. So you can find papers back to in the ICSOBA proceedings and other sources. That's it. Thank you.
Yeah. That one question here, goethite conversion to hematite or maybe to removing point of view, is they're doing anything research on it, how to remove completely? Of course, completely is impossible. It's interlocked. Is there any specific paper or maybe detailed study if that's really going to be very good, helpful for the bauxite point of view? For the
Sorry, these are iron minerals and bauxite. Anything you do, it adds up the cost. And the IBAAS process is the best beneficiation process, which removes all the iron minerals. You cannot remove goethite. If you go to remove goethite, hematite, your cost of bauxite will become $150 equivalent to alumina prices. So all the economics plays a very important role.
Yeah. Of course, we can't remove completely up to a certain extent to make it reasonable.
It's only physical process. If you can do something, there are a lot of tests have been done. It is not easy to remove goethite and hematite. It's all goes along with the gibbsite. So it's quite difficult. And actually, IBAAS process is actually chemical beneficiation process, and that can only remove this goethite and hematite.
Yeah, that's
okay.
Okay.
Thank you.
Yes, yeah.
Thank you. Thank you very much. Thank you. Thanks, George. We will meet again. Bye.
Thank you for your attention, ladies and gentlemen.
Thanks. We'll meet again.